Relatively soon. Audrey just told me that there's a few people that are still finishing up their breakfast, and hopefully they'll be joining us, at least a few more folks. But let me go ahead, and as a way to get us started, let me introduce myself, since unfortunately I missed the opening session. I was in transit, but I am Steve Richards. I'm the director of the Southeast Transportation Center, the newly awarded center. Last year, we head up a consortium of 9 universities total, with the University of Tennessee as the lead institution. Our theme is comprehensive transportation safety, and I'll see if I can rattle off our 8 additional members in addition to the University of Tennessee. We have the University of Kentucky. We have 2 institutions in North Carolina. We have North Carolina A&T University, and we also have the Highway Safety Research Center at UNC Chapel Hill. We have 2 Alabama schools. We have the University of Alabama and the University of Alabama Birmingham, which are well represented in today's session. We have Clemson University in South Carolina, and then we have 2 Florida universities. We have the University of South Florida, and we have the University of Central Florida. And we feel like this gives us a very strong team in comprehensive transportation safety. Actually, the University of Tennessee, in past competitions, have been the lead institution in several winning competitions, so we're not new to this game. We have been the lead institution of the Southeastern Transportation Center for a little over 15 years, beginning in 1994, and of course we lost the immediate past competition, but are most happy to be included in this round of UTC program. As always, we're looking forward to working with all of our university colleagues and the other UTCs within our region, and particularly the other safety UTCs in our region. And there's a few of those, but then also the other safety-related centers throughout the country. So with that, I'll stop talking about myself and get our session started. This session today is going to focus appropriately for me, because it's my background in transportation safety. And all of our papers today, they look like they are outstanding papers, and I know our presenters will do a very good job presenting those. And so let me go ahead and get started with our first paper. The title of that is Traffic Safety Impacts of Digital Roadside Advertising in Alabama and Florida. And our presenter today will be the lead author, Virginia Sisiopiku, and I'll let her acknowledge her additional authors on that particular paper. But let's welcome Virginia as our first speaker today. Speakers, before we get started, Jing is our technical support person, so if you're feeling a little uncomfortable or have difficulties, just look over this way and he'll help you out.
If you have any questions,
well, it's my great pleasure to be here with you today and talk a little bit about the work that we are doing on traffic safety impacts of digital billboards. I would like first to say that this project is sponsored by the National Center for Transportation Productivity and Management, a mouthful, and also the Alabama Department of Transportation and Florida Department of Transportation. I would like to start by acknowledging the contributors to this project, my colleagues. They are listed here, Dr. Hallen, Dr. Jan, and Dr. Galuri from Florida International University, and Dr. Stavronos from UAB, and Mr. Islam and Mr. Salva. So we have a good team working on this topic, and I think it's quite interesting because there is an ongoing debate about the potential risks from advertising billboards. And it is true that studies show that if there is distraction, the driver is more likely to have an accident. In fact, it doesn't take long, just taking the eyes from the road for 2 seconds has been estimated to increase the risk for an accident by 23%. So what our team wanted to do with this project is to investigate the potential links between digital advertising billboards, distraction, and traffic safety. So we wanted to have a comprehensive approach to tackle this issue, and we structured our study in 4 sub-studies, if you wish, the 4 tasks that you see here on the screen. The first being a detailed state of practice synthesis. Second one is surveying the perceptions and attitudes of roadway users. Third one, driving simulator study. And finally, an epidemiological study looking at crashes associated with billboard presence. Let me say by definition, billboards actually are trying to distract the driver. So they are trying to take the eyes off the road and to the message because they are advertisement. These features that the digital billboards in particular have that I have listed here on the slide, they make those devices good for marketing, but potentially harmful as far as traffic safety is concerned. Compared to the static billboards, the digital billboards actually are changing frequently, so that may distract the drivers even more. They have more realistic images, and also they have often they actually request for the driver to do something else, more advanced ones, so potential interactivity with the driver can pose additional risks. So we started with trying to find out what is known so far. So we did a really in-depth, comprehensive literature search and synthesis. Looked at studies that were published both here in the States and overseas. And I would say from these, we found a lot of interest in this area, but the results were still non-conclusive. There was evidence that there is a connection between digital advertising, billboards, and driver distraction, but the jury was still out of whether or not this distraction was really causing additional accidents. I think it's fair to say that there was some concern about some of the studies because, you know, some of them were actually funded through the outdoor advertising companies. So that was one thing that really was not a good thing in our view. Another thing that we found out is that all these studies really suggested that local conditions may play a role. So the only thing that the studies agreed upon was that additional research is needed in order to have a much more in-depth understanding of the connection between digital billboards and traffic safety. So addressing these concerns, we started with a survey of users. That was an internet-based survey that aimed at understanding better the perceptions and attitudes of drivers toward the use of billboards in general and digital billboards in particular. We ran this through SurveyMonkey. We had 22 questions that collected some demographic information about the exposure of the drivers to both driving and driving in areas where these billboards are present. And then we asked specific questions about perceived safety, whether or not the drivers would look at those signs in detail, if the messages were useful, and also if they felt that there should be more regulation with respect to the placement, the size, and so on of some signs. As far as the responses are concerned, we ran this in Alabama and Florida, and we got 295 responses in Alabama and 340 in Florida, which is a very good size, I think. So today I'm going to present just a few of the results, focusing on the Alabama drivers only. We asked the participants of the survey if they felt the billboards were distracting in general. 46% agreed that they are distracting, and then 68%, more than two-thirds, actually suggested that the digital billboards are more distracting than the regular billboards. We also asked them if they slow down as they approach a billboard in order to be able to read the messages, and 88% said that they never slow down. We also wanted to see if those billboards are actually offer a real marketing benefit. So we asked one question related to that to see if they are using those messages, and more than 75% suggested that they hardly ever use those messages. So that's something good to know. After looking at the data, in an aggregated manner, we wanted to see also if there are differences between different age groups or the different sexes and so on. So we did some additional analysis. This, for example, is focusing on how the responders responded by age group. At the bottom of the slide, you can see there that the younger age group actually suggested that the digital billboards are more distracting than any of the other age groups. We also looked at similar, we did some additional analysis based on different ages. We asked the question, do you look long enough to read the entire message? And also, do you slow down as you approach the billboard in order to do so? And not surprisingly, again, the younger demographic suggested that yes, they look, they really read the message, but they don't slow down, which may be also an issue of concern. Overall, I think the consensus was that the digital billboards indeed are perceived as being much more dangerous than the static ones. And in questions that we asked related to regulation, overwhelmingly the sample that we surveyed suggested that there is a need for stricter regulation as far as the position of those billboards, the sizes, and so on. Which I think it's quite an interesting finding. The next part of our study focused on driving simulator study, and the idea was there to really observe drivers as they were driving in a controlled environment. We used the UAB driving simulator to do that. Dr. Stapinos, who is here, is leading this effort. We actually had to go through a series of steps, as all driving simulator studies need to develop first the data collection protocol, then we had to develop the actual testing scenario. What we used was a 16-mile long roadway segment that was divided in 4 sections. Each one of the sections had different options: no billboard, static billboard, and then digital billboards with 200 to 52 and 500 feet transitions. A lot of effort went in recruiting participants. We recruited more than 60 participants. 57 of those were included in the study, and they were classified in 3 major categories: the younger ones, the young teens, the middle-aged, and the more mature drivers. So then we proceeded with the data collection and analysis. Our attention focused on these 3 different aspects: the length of eye gaze, how long the subjects were looking at the digital billboards over the time of the experiment, memory recall and recognition, where we how the subjects actually remembered what they saw in the digital billboards, and if they were able to recognize correctly billboard signs that they were in the experiment when they were mixed with other signs that they were not present. And finally, driving performance, where we focused our attention on the number of speed limit exceedances. Speed limit was set at 65 miles per hour in the experiment, and there were signs as the drivers went through the simulator to reinforce the speed limit. So drivers that went above 69 miles per hour were recorded. Also, we looked at the number of times the driver actually deviated from the straight path and the total number of vehicle collisions. Here I only have a couple of results, for example, from the simulator, from the driving performance analysis. There. We looked at the different age groups and to see if they were behaving differently. It was seen that participants, surprisingly I would say, had fewer speed exceedances when there was a billboard present. Maybe that indicated the fact that they were really paying attention to that billboard, and instinctively they tried to not to run too fast. And not surprisingly, when we compared different age groups, teens had more speed exceedances than middle-aged and older drivers in all types of cases that we studied. The last component of our study was an epidemiological study that looked at the crash rates in the vicinity of billboards. We started with identifying appropriate sites both in Florida and in Alabama. Then we developed a methodology to determine what is the actual area of influence of, or potential influence of a billboard. The FIU actually did a field study where they drove a vehicle and took pictures to see, how far back actually you have to be in order to potentially be affected by the digital billboard. Based on this, we were able to define what we have here as the area of influence. You will see here what we call upstream is the area of influence of the billboard, which is the area immediately upstream, and then just a little bit further downstream because the impact may actually still persist for up to 0.05 miles. And then the area that is listed here as downstream is the counterpart, if you wish. So we have a pair of sites at each location, so we compare what are the accident rates that were observed upstream in the area of influence versus immediately downstream from the sign. As I mentioned, this was done based on crash rates. Like with the equation down, it is the number of crashes over the AATT, the length divided by the length of the road, and the number of years of analysis. We used 3 years of analysis in the Florida case, 2009 to 11, in the Alabama case, 2010 to 12. And here are some of the results from the Florida sites. We have 10 sites there, 10 locations. As you can see on the screen, the length. First we have the upstream, which is the actual area of influence of the billboard. I have the mouse. Okay, so you see for each site we have the total crash count during that 3-year period. The AATT, then we calculated the crash rate, and then we did the same for the counterpart, the downstream section, and then we looked at the percentage change. What you can see from this particular table, you can see that some of the sites actually had more accidents downstream and some had fewer accidents downstream, which was expected. But if you look at the total number of crashes, when we compared the crash rates for the area of influence of the digital billboards versus the area of non-influence, then we saw that we had almost 25% more crashes in the area of influence, which I think is a very significant finding. Some additional analysis also focused on the type of crashes that we observed. Again, with this paired comparison, we noticed that we have twice as many actually side sweep and accidents with crashes with fixed objects in the area of influence of billboard signs, which again shows that those signs may actually have contributed to the increased crash rates. This study is still ongoing. We are completing now the analysis of the data from the survey for the Florida drivers, and we are also completing the Alabama portion of the crash analysis. We think that definitely the study looked at a more comprehensive way in the issue of traffic safety and digital billboards, and gave us an opportunity to raise awareness about this issue, where we really think our contribution would be, after making the case, in front of the authorities and in front of the colleagues and the general public, is really to be able to influence policy. I would say that regulations of the billboards are primarily done having the static billboards in mind. So we hope that this kind of research will bring more awareness and will show that some updates in those regulations are needed in order to take under consideration the additional impacts or the additional, the special cases that we see when we have digital billboards in place. And with that, I think my time is up, so I will wrap up here and ask if there are any questions or comments.
We do have time for a question or two.
Yes.
Did you vary the light density for the billboards? For instance, the GDOT shut down one on north of the Beltway because it was too bright, but the Georgia Tech board is still up and still lit.
Yes. We didn't change this in our driving simulator study. Obviously, the other studies we don't have control, but I think this is exactly one of the issues that one would have to take under consideration as we propose the new regulations for those signs.
First, thanks for a great presentation. A couple of comments. One, I guess, is another argument for automated vehicles. So we can look at all the billboards we want, tax all we want. The upstream and downstream comparison is good and interesting. I wonder if the study also incorporated differences in the grades of the road. In other words, it would seem to be more dangerous situations when you're going up a hill. You don't see what's going on the other side of the hill. You get distracted. By the time you come back, boom, you're on top of the hill. There's all sorts of bright lights, and you just need to know what's going to happen, as opposed to a flat road where you can take your eyes off the road for a second or two at a time. You can look at your speedometer, look at your gas, whatever it is. But when you're going up a hill, that's the most dangerous spot. I wonder if the study incorporated anything of that nature.
No, we didn't. We chose our sites so that the signs were visible from the distance, just so that we can see the progression, of the driver and so on. But yeah, there are special cases. Typically, at least in the locations that we have identified in Alabama, there are very few of those cases that you mentioned, just because the digital billboards are relatively few compared to the other billboards. I think even the advertising companies choose to put them in strategic locations so that they don't really, that they have the greatest impact possible. But it's definitely a very good comment. So I would just to take it from there, say that the geometry and the special conditions still, you know, need to be looked at. And this is a very good example of a special condition that may actually have even greater impacts. Thank you.
Just one more question, Jeff.
I was just curious, when you did the simulator study, were participants briefed in any way as far as what they would be asked afterwards? Because I'm curious, if I knew I was going to be tested, for example, on the content of the billboards, I would pay more attention to them than perhaps I would in a normal driving scenario. In a normal driving scenario, billboard can pass and I would not be distracted by it, but if I'm told ahead of time I'm going to be tested on that, that would
And
affect
it
my
is a very
behavior.
good point. So when we recruited the subjects, they had no idea that it would be a study that relates to billboards at all. So of course, you know, we met with the subjects before and they had to go through, you know, make sure that they had driver's license and things like that. So we met with them earlier, but no, they didn't know, so they were not alerted. We asked them to drive as they would normally drive. But then, you know, in the debriefing then, you know, we asked some additional questions. There was another question here asked, you know, about their attitudes and so on. It is a very good point, but we took care of it. Yes. Thank you.
Thank you, Virginia. And I think I forgot to mention this. I don't have a lot of introductory materials to go through, but Virginia does head up the transportation faculty group within their civil engineering department at UAB, and we're looking forward to working with Virginia and other faculty members there at UAB as part of our new STC. And also, you can probably tell from her last name about something about her ethnicity. And so if you look at the program here, it looks like the Greeks are taking over the transportation profession. With that, our next paper is entitled Investigation of the Effects of Drivers' Body Motion on Traffic Safety. And it will be presented by Alexandra Kondyli. And Alexandra is a postdoc from the University of Florida, and she's got two other authors, and I'll let her acknowledge the other authors. Let's welcome Alexandra to the podium.
Thank you very much for the introduction. I would like to acknowledge my co-authors. The PI is Dr. Anthony from the University of Florida Digital Worlds Institute. He's now here today in this presentation. The co-PI is myself and Dr. Virginia Sisiopiku from UAB. And as you heard, the topic of this project is investigating the effect of drivers' body motion on traffic safety. And this is a project that we started last October. It was funded through STRIVE, and it's still an ongoing research, and we are expecting to finish this project by the end of the year. So a little bit of an overview of my presentation. I will make a brief introduction to the research and the research motivations. We'll briefly discuss the methodology and then the data collection plan. Then I will present to you some preliminary data analysis that we have completed so far. And I will close this presentation with some preliminary conclusions and then the next steps of this project. So introduction and motivation. Driver assistance systems, everybody knows what these systems are, and they're very, researchers have been involved with these systems. So these systems typically include radars, lasers, sensors, or video sensors. But these systems typically are focused on the location of the vehicle. They're trying to find what the trajectory of the vehicle is and what is the location of the vehicle along the roadway. These systems are not focused on what the driver is doing. So, and we know that driver behavior is the key factor that affects safety. So the focus of this research is to look at what the driver is doing, because what the driver is, but if we can look into that, then there are ways that we can improve safety. So by examining the driver body posture, what we want to do is we want to provide some answers to some key questions, such as what kind of cues can the entire body posture provide us related to safety? And also, how can we classify what is a safe or an unsafe driving condition? And how does these conditions vary by different drivers? And also we want to ask what can we do in order to help drivers be more alert of their surroundings? Is it something that has to do with a better training, or is it something that we need to change the vehicle economics possibly? Or is it something that the driver assistance system can look further into? So for our experiments, we are looking at the driver body posture by using some low-cost infrared depth sensors. So these depth sensors, like a typical depth sensor, is this Microsoft Kinect camera, which is an infrared projector and an infrared camera. What these sensors do is they create a 3D mesh of real conditions, and it's also good because you can have the 3D image of real conditions, but you can also overlap, because it's an RGB camera, you can also overlap with real image of what's going on. Apart from that, the Kinect can also give the skeletal tracking, so it can give you what the skeleton is for each individual, is identifiable immediately, and that's something that is very useful for our purposes. Now, a little bit of how we're doing this study. What we want to do is we want to identify patterns in the way that people drive, and the way that the people position their bodies in the vehicle when they're doing specific maneuvers, such as when they're merging or when they are changing lanes, and also when they are involved in secondary tasks. And with that, we want to correlate these specific maneuvers with what the drivers were actually looking at, and also what there was actually out there in the field by having information from the video information from the environment of the vehicle. So how are we going to do this? We will do a naturalistic type of data collection. So we want to have a total of 40 participants with ages that range from 16 to 65. So we have very novice drivers, but also more elderly drivers, and of course there is a middle age range in that. Right now we're in the process of the field data collection. So we have 15 participants completed the studies so far. And what we are collecting is we have the observation of their upper body posture, and we have information of their eye movement, their eye gaze. What we are doing with this field experiment is we are asking the participants to merge on the freeway. This is I-75 in Gainesville. This is a major arterial street in Gainesville as well. And we asked them to drive on the freeway, merge, exit, then merge again, and then also drive on an arterial segment, do anything. Some people do change lanes, and they have to do this for several runs. Apart from this field, this roadway experiment, there is also a parking lot experiment. We tell them to drive around the parking lot and text while they're driving. Of course, we couldn't let them do that in the freeway. They will be not beyond us. And we also ask them to see how they do their parking maneuvers on the parking lot as well. And the total experiment duration is about 2 hours for each participant. The instruments we're using for this field data collection is we have an instrumented vehicle at the University of Florida Transportation Institute. It's equipped with a GPS, and it has some cameras that face the front and the back So we have video feeds of what's going on when our vehicle is driving along the roadway. And we also have installed inside the car the Microsoft Kinect to have the 3D body posture animation, and this is connected to a laptop. And we're also using some eye tracking glasses to get the eye gaze of the participants. These are also connected to a laptop. So we have 2 laptops and several equipments in one car and to do the data collection. Now, this is where we are right now in the process of collecting data, but we have already completed a pilot study a few months ago where we wanted to see what exactly we're looking for and how can we process the data we're getting from the body, from the Microsoft Kinect, how we're going to use this data. So for that we did a pilot study a few months ago. We had 4 participants, 2 male and 2 female. Actually this is me, and this is the PI, Dr. Barbutis. You can imagine who the other 2 are, our spouses. So we had, at that time, we had only the Microsoft Kinect available. We didn't have the eye tracking. And we installed the Kinect and we ran on I-75 again for 20 minutes, then on an arterial segment. And we did the same kind of driving, like merging and lane changing and things like that. So each one of us drove for 20 minutes. The Microsoft Kinect needed to be calibrated in order to have this short range because in the car space is very limited. This is an example of a video of what you can see the PI driving. You can see how it looks like the 3D animation. It can capture most of the body, of the upper body at least, while he is driving. Now for the data analysis, during the pilot, like I said, we have identified a few measures that we need to use for evaluating the driver behavior and also for identifying these patterns of the driver upper body posture. These metrics that we have looked at are some global statistics such as the mean and the standard deviation of the depth value of each pixel that the Kinect gives us across time. The second measure has to do with the skeletal model, so look at what the skeleton is doing, and also look at the orientation of the torso of the drivers. And the third one has to do with identifying the direction of movement and the associated magnitude for other parts of the body as well. So, for example, here you see some figures of emerging maneuver and also some images of emerging maneuver and of exiting the freeway. And in these images, it's depicted the mean depth value and also the standard deviation of the depth value. And with the gray color is actually the surface that is being produced through the 3D imaging, and this is the mean value of these pixels, and with a color coded, the red, you can see the standard deviation during that specific maneuver. So you can see that, for example, there is some movement during the merging. You can see like the top of the head that it has been tilted a little bit, and of course the hands. And it's more obvious during the exiting maneuver, probably because there was an entire loop that we had to drive in order to exit, so the movement of the hands were a lot bigger. So larger standard deviation is of course associated with wider range of the body motion. So this is the mean and the standard deviation are useful because we can look at there may be differences between different drivers, and also it also depends depends on the task that the drivers they are performing. If they're merging or if they're changing lanes, you can have different values for these metrics, both for the mean and for the standard deviation. Another thing that we're looking at is the representation of the driver skeleton. So this is in the left image, you can see the skeleton of myself where I'm driving, and this can be a real-time actually representation of the skeleton, and it gives us 3D coordinates for all these points. So you have 3 points for the hands, 2 for the shoulders, 1 for the neck, and 1 for the head. And we can actually use these points, these 3D points, in order to better manipulate the data that we have. And you can see in the right side that there are 2 drivers, and we have for each one of those 2 drivers, we have identified 7 points along their body, so hands, shoulders, and also their neck. And if you just look at where if you create this triangle between the points of the shoulder and the neck, you can have actually the orientation of the torso. So if you just look at this triangle and see how this triangle rotates in space, you can see how the torso is actually how drivers are turning their torso. So this is some clear examples of the differences between 2 drivers when they are changing lanes. This one has a lot more distinct orientation, rotation of the torso. And this is another example of a merging maneuver. This case where you can also have a graph of this of the torso orientation before, during, and after this merging maneuver. And this is the orientation is like the reference point. The 0 degrees is actually when you're completely parallel to the steering wheel. We did this for 3 of the drivers of the pilot study, and when they performed similar merging maneuver at the same location, and you can see that these profiles are different for all 3 of them. Some have like a very minimal movement of their torso, some of them have a very great movement. Now, another way of looking at this is to look at, in general, the rotation and the direction of movement of other parts, such as the arms and the head. So it can actually be, we can actually have something like a heat map of how the head and the arms are rotating when we are performing, when we are driving. So here, for example, with red is the color that it's closer to the kinect, so it's like the brighter, and with the blue color is the ones that are moving away from the kinect. So you have these different colors, color-coded images. So we have actually used for a specific merging maneuver again, we have found what this rotation is for the arms and the head of the 2 drivers. And you can see that there are some very distinct differences between the drivers as well. For example, the head activity of the second driver is a lot more intense than that of the first driver, as well as the arm activity. And it's possible because it may be due to driver behavior, or maybe also due to different traffic conditions. You might have this in this particular driving case. There might it's possible that there may be vehicles in front of the or around the driver, and that caused the driver to be a little bit more alert of their surroundings. So to summarize finalize this research, we're proposing a novel approach for assessing driver activity inside the vehicle. And we have developed some tools to investigate how different drivers perform these various maneuvers. And we want to investigate which of these driver approaches may eventually lead to some unsafe conditions. And we have identified some quantitative measures that are going to help us to quantify this, the body posture and the implications on traffic safety. So the next steps is to complete the naturalistic type of data collection effort, and we want to apply the methodologies for analyzing the observations from different drivers and under different maneuvers that they are performing. And we will use the information from the eye gaze and also from what actually the drivers are looking at, what actually the conditions are outside the vehicle in order to identify potentially unsafe conditions. The purpose of this is to provide some kind of guidance related to training of drivers and see how well this system that looks specifically for the driver can fit within existing in-vehicle driver assistance systems. That was if you have any questions.
Yes.
I noted that you cut off driver subjects at 65, yet us seniors are living longer, becoming in the fastest growing cohort of the population in drivers. So why did you go beyond that? Secondly, did you clock the education of the various people? Because us transportation engineers are a lot more comfortable with driving situations than those that are not, or those that really haven't got, have just gotten out of high school.
We're not looking at the background of the participants. We don't want to limit what the participants were getting, so we want to have a broad range of participants in terms of their educational background. And related, concerning the age, you're right, we need to have more drivers that are above the age of 65, and what the advertising that we did, at least from the data that we have so far, we only have participants that are up to 65. And now we're making some effort to get some participants that are above that age as well.
I don't know if there's ways, if you have ways to impose your body movement analysis techniques straight to video, but have you considered to increase the population of subjects mining naturalistic driving study database that is being developed, or that has been developed through the Shark System?
We haven't thought about that. But that's something that maybe we can discuss as a follow-up.
Yes. Yeah, why don't we try to use the mic? I think I can walk around with this one a little bit easier. We can minimize the static.
A technical question. I've heard of people having some difficulty with IR sensors in different sunlight conditions. Did the Kinect ever wash out while you were using it, or was it good?
The Kinect works perfectly fine with any sunlight conditions if the windows are closed. If there's a lot of sunlight and the windows are open, yes, then we have problems with that.
We do have time for another question or two. You've got a loud voice. Go ahead.
I'm still uncertain, how will you determine what is an unsafe body position or maneuver? I'm just thinking that some people have better peripheral vision and they don't have to move as much as other people who might have to move to better job of the mirror settings or whatever. How will you take what you're gathering and say, okay, you don't want to do this, and you do want to do that?
It will have to do with when they are moving their body, what they are missing from the entire environment, because it takes some seconds to go from this to here to back to the initial position. So within these seconds, we have the information from the video that is looking straight ahead. So, but the driver does not have this information of what's going on in front of them or what's going on, you know, in the other side. I believe that these seconds are important to identify if there's something that is going to be unsafe for them, if it takes them too long to focus back on the initial posture.
Are you considering the probable familiarness of the driver with the area? Because sometimes if you are aware with the area, probably your movement will be very less compared to if you are taking a new ramp or something. You might be moving more. So are you considering that?
The participants are all from Gainesville, so they're all locals, these are very areas that are highly driven. So most of the population drives around these areas.
Anybody else? One more question in the back.
So another technical question.
Let me bring the mic, because you're far enough away from the camera. I know it might have a hard time picking up your question. Thank you.
So another technical question about the Kinect. Do you know what kind of sampling rate were you guys able to obtain from that device?
I don't remember. I think it's something in the order of 60 hertz.
Okay, and that's the limitation of the device, right?
Yes.
Okay, thank you.
Anybody else? Thank you, Alexandra. Okay, our next paper is entitled Factors Influencing Visual Search in Complex Driving Environments. There's a number of authors, and I'll let the presenter acknowledge those. And our presenter today for this paper will be Aaron Greenwood. Aaron is a PhD student at Georgia Tech, and he's originally from Winston-Salem. And I said, you don't want this? Is it
Maybe looking at the screen. Let's see if I can get this to it. All right. Can everybody hear me? Is that mic working at all? Yes. Anyway. Okay. I'm Aaron Greenwood. I'm going to be talking a little bit today about factors influencing visual search in complex environments. A lot of authors on this. My supervisors back in there. Michael Rogers, Greg Corso up at Moorhead State in Kentucky, Anzu, me, Shaw, and James Bay, who I actually forgot all the others. Sorry. So big picture, any Redditors, TLDR, make any sense to anybody? Just remember these things as we're moving forward. It's a good way to keep track of what's going on. Continuity matters in terms of these devices. Anytime you have several devices, the linearity of them is important. Closed versus open divergence we found was very important. Work zone activity makes a difference, and underlying spacing of the devices is not critical. This is not going to make any sense to you right now, but keep them in mind as we move forward. A quick outline, just an overview of the project, the background on the problem we've been looking at, a quick methodology to get through this, some of the results that we've got, and a little discussion on that, and the ongoing research that we've got going on to keep looking at different visual search patterns. So background. As we were driving through a lot of work zones, and GDOT brought this project to us too initially, we realized that we may have a problem with dazzle camouflage. Now, if you're familiar with dazzle camouflage, it's the idea that you're you're never going to be able to hide a large object, so you may as well just confuse the people around you. So we used this in war in World War I, pre-radar and sonar, as a way of keeping U-boat captains from being able to hit large ships. You're not going to be able to hide the ship, so you may as well hide where it's going. Zebras do this in nature. You're never going to hide a zebra on the savannah, but you are going to be able to hide where it's going or individual objects. So the question we're asking, have we camouflaged our work zones? Have we made them so visible individually that the overall message is lost? And so we're looking at some of the visual search patterns as you move through these complex environments as to how that impacts your vision. So in order to get a sense of what some of these principles might be, we looked back into the psychology and even artistry literature and looked at the Gestalt principles of grouping. And there's 7 of them: proximity, the closeness of objects; similarity, so how similar objects are; the continuity, so the linearity of them, are they in a straight line; closure, do they overlap; symmetry, and figure, ground, and common motion are quite as important because they deal a little more with motion. So here's an example of some of the objects you may see. Proximity, you can form 2 groups very quickly with your eyes because those 2 groups are much closer. Closure, you form that as a single group because they overlap. And continuity, you find a straight line in there. One of the problems with this, though, is that you may have seen a different straight line, which is a problem with work-zone devices. And sometimes our intentional patterns are not the ones that are perceived. So, a little bit about our introduction. We needed to very quickly identify some of these principles to move into some more resource-intensive simulator tasks. Our need to screen that led to a strategy of developing some 3D environments and essentially just showing a lot of still images to individuals and having them do a manual visual search task. Find an open exit ramp if it's open, click a closed button if it's closed. And we were able to present a lot of images with a lot of different scenarios to different participants and get their feedback very quickly. So we ran ultimately 3 experiments. The first were sort of clean images, just the horizon line, the ground and the sky, and then the diverges. And these work zone devices. Experiment 2, we based some of the results on experiment 1 to develop a novel treatment, which I'll go through. In experiment 3, we sort of increased the level of complexity. We sort of suffer from the infinite detail requirement in applied science, where you can continue to add as many levels of complexity or specific situations, but we wanted to come up with a good generalizable result out of this. So we wanted to at least move a little ways into that research space. We developed this in compliance with the UTC standards on lane closures and exit ramps. Actually, some of this is not physically possible to do, so the standard actually lists some distances that would make lane widths about 2 feet wide. So we adjusted accordingly based off of state standards. So our first experiment, we ended up showing about 900 slides. We had 41 participants. 2 were excluded because they just sat and clicked and they didn't actually respond to any of the questions, which is one of the perils of psychological research. We showed these images in a random order to each participant, and we used alternatives of 10-foot drums, which I'll show you in a second, but those are the distance we observed in nearby states. 40-foot drums, which is a drum every skip line, which is what we observed in Georgia. 40-foot drums with a little error, so plus or minus 2 feet in the X and the Y direction. And that was randomly generated. PCV portable concrete barrier, and then no work. We used 5 distances and 2 geometries. One where the freeway curved to the left, and one where the freeway continued straight and the exit to the right. 10 repetitions, 900 slides. We actually heard participants moaning they were so bored they were going through this, but isn't that the point? We want people to be a little tired by the end of that. So those 10-foot drums look a lot like this. 10-foot drums plus or minus 2, a little bit of variation in there, which is a later alternative. 40-foot drums, a little more spacing. There we go. A little variation in there. We're going to have to stand here and do this. I think this battery's dying. The portable concrete barrier. And then using some of those results, we made a small variation on this using similar geometries and distances, but we added a device called what we call the linear channelizing device based off of that. So it brought the continuity and the closure out of the portable concrete barrier, but not sort of the opposing aspect of it. To see if the principles that we designed this were what was keeping people understanding, or was the sort of fear of the large concrete barrier. And then from those results, we worked on experiment 3, where we added the no vegetation, light vegetation, trees on the left, trees on the right, trees on both sides, trees on the right and the median, and then we added a few pieces of work zone equipment into that random mix to make sure that those would work. So in terms of data reduction, we developed certain zones that if a participant clicked in, we categorized their response in a certain way. Those zones in the bottom left over here was where we had our exit closed signs. If they clicked here, they were indicating that they thought that the ramp was closed. This zone is the ramp itself. This was the active work zone. And up in the top left was a little button that said don't know. So if they just completely had no idea, they had an option to bail out essentially at that slide. So you can see varied responses. This is a representative slide. And this was closed, but a good number of folks clicked in the active work zone, indicating that that's where they thought the exit was. So some of the results, in terms of curve, these graphs are a little unwieldy, and I apologize for that, but I'll talk through them. Experiment 1, we essentially saw the correct response rates are going to be along the top, and the errors and types are along the bottom. Not a lot of difference with the curve, and a lot of that was driven by the line of sight. You could see all the way to the exit by the end, so we didn't see as many errors in that situation. Where you did start to see issues was in the straight conditions. The freeway is continuing straight along. Those are the images that you were looking at. So what you see is sort of 1 second away from the ramp. We're very close up, not a lot of mistakes. Most of the mistakes are driven by the plus or minus 2 on those drops. So a little bit of variation makes a big difference. As we start moving out, 2, 3, 4, you start to see that the error rates start to climb. By 5 seconds, pretty much sort of all over the place. But what you consistently see is that the drums underperform the portable concrete barrier. And that sort of led us to some of the conclusions that we saw. And in fact, you'll find what's another interesting result is that 10-foot and 40-foot drums do about the same just about all the way through. So the proximity of these devices doesn't matter as much as the placement of the devices, which was a result we were not expecting. So again, yeah, portable concrete barriers perform pretty well under all conditions. The longer distances, you have smaller, or just a small variability in the barrel placement, so plus or minus 2 feet. And not always up to 2 feet, so we're in some cases talking a few inches. Can have a pretty significant effect on the accuracy of the responses. When the ramp was closed, individuals found that that was a more challenging alternative. Straight was a more challenging geometry, as we saw. No significant differences between 20 and 40-foot drums. And so what we wanted to do there was develop a new treatment for characteristics and additional variability, which again is that linear channelizing device. So if we look at experiment 2, you can see pretty similar results in 1 second. People not messing it up. Everybody's able to see the exit ramp and make a good response. By the time we get into 5, some of these drums 10 feet plus or minus 2, so they're getting very tightly spaced, but sort of almost created an effect of a sea of drums. We're getting response rates that are correct in the 20%, some 25%. So this is worse than guessing, almost. And that can be an issue, especially when you're talking about the linear channelizing device and the portable concrete barrier doing very well. And these purple zones actually said that they kind of clipped a little to the left of the freeway. So that's a categorization error that we think we might have too. So these are doing very well, even in the 5-second mark. When they're closed, you see pretty similar results too. Where the errors are with the drums. And the linear channelizing devices and the portable concrete barriers are doing much better. So results are here. The portable concrete barriers doing much better performance. Again, the small variability makes a big difference. What was great about this is that these linear channelizing devices and portable concrete barriers have very similar performance. So we feel that the principles that we've extracted from that for the design of those devices makes are functional to them. For experiment 3, when you look at it by alternative, you see almost same story here. It's the drums with the small variation that are creating most of the errors. Interestingly enough, drums with 40 feet still doing worse than the portable concrete barrier and linear channelizing devices, but not quite as bad as you would expect. It's just a few seconds out that you really start to get that, you lose an understanding of what's going on with the first sound. And same results are with the closed condition. It's the drums with the small amount of variability that make the difference. When we looked at it by equipment, we found that really the equipment didn't make as much of a difference. In the closed condition, not having an equipment led to more errors in that situation. We think that the equipment is essentially cueing people that the ramp is closed, which is helpful for keeping some of those down. So that may lead to future research into issues with empty work zones, but it's something we need to consider for that. Similar situation when we're looking just at the drums. That's where you see most of these errors from having no equipment. By vegetation, we found that really there was no effect from the vegetation. A small decrease in errors when there are trees in the median, but we're not entirely sure is the mechanism behind that. So again, portable concrete barrier and linear channelizing device performs the best performance here. Small variability. Barrel placement, again, same story as experiments 1 and 2 there. And the impact of vegetation really didn't have a strong issue with the presence of the activity in work zone. Could increase people's understanding to understand the exit closure. So again, now we're back to that big picture. Continuity matters. We found that the devices that had the continuous characteristics had the best performance, were less likely to lead to errors. Closed versus open had very different responses. If you notice, the rates were different. People tended to bias wanting the exit to be open and would click into the active work zone. And that was one of those results. Work zone activity makes a difference, so the amount of equipment that was around impacted, especially in those drum alternatives, whether or not somebody could identify that the work zone was closed. And then the underlying spacing, so the difference between those 10-foot and those 40-foot drums really didn't make a difference. It was more about the placement of the drums themselves. So what are we doing moving forward? We're moving this into driving simulation. Now that we've got a good understanding of the principles and the designs behind that, we're using remote eye tracking and some of the new SAE Jig. It's actually 2944, sorry about